Since the beginning of spaceflight, over 9,000 satellites have been launched into orbit. But with the rate of launches increasing exponentially, space is about to get much busier. In addition to every satellite currently in Earth's orbit, there is around 100,000 tons of debris, most of which is too small for us to track. But how much damage can a tiny object really do to a spacecraft? And how do we shield the ISS from such dangers? In this video, we're going to look at the powerful physics behind space impacts. We're also going to look at the different methods used to shield the ISS and how we put them to test here on Earth. Out of all of the objects hurtling around Earth, only those larger than a baseball can be tracked. If a spacecraft is on a path to collide with a piece of debris, it performs a maneuver to avoid being completely destroyed. But for the millions of tiny objects that can't be tracked, a collision could still be catastrophic. A raindrop weighing 0.2 grams will fall on your head with about 0.8 millijoules of energy. But the same raindrop flying around as space debris would have over 1 million times more energy, even though its speed is only 1,000 times faster. The reason that velocity makes such a difference here is because in the formula for kinetic energy, mass is directly proportional, but the velocity is squared. This is obviously nothing new to scientists, but when operating in the vacuum of space, these tiny impacts are unavoidable. Even things like flecks of paint have led to visible impacts on the windows of the space shuttle. Micrometeoroids coming from outside of Earth's orbit can be moving at even greater velocities, like 20 kilometers a second. Since the ISS is the size of an entire football field, it is constantly in the firing line of debris. While on board the space station, astronaut Chris Hadfield took this photo of one of the solar arrays with a bullet-sized hole right through it. In order to shield something as large as the ISS, rather than using heavy, thick plating, it uses something called a Whipple shield. This consists of a thin outer wall, followed by a small gap and a thick inner wall. The outer wall doesn't take much speed out of the impact, but it shatters the projectile into much finer pieces. This means that the kinetic energy is spread out into many smaller impacts on the inner wall. In some areas of the shield, the space between the two walls is stuffed with a high-impact material such as Kevlar or aluminum oxide. On the ISS, there are over 100 different shield configurations, as a balance needs to be found between the weight and the amount of protection. Fortunately, we're able to do a great deal of testing on these types of impacts here on Earth. Since a typical firearm can't generate orbital velocities, scientists back in the 60s invented something called the light gas gun. This works by using an explosive charge to move a piston and compress a sealed chamber of gas. The end of the chamber has a thin, bursting disc scored with a cross which bursts at a specific pressure. Once it bursts, the rapid expansion of gas accelerates the projectile up to orbital velocities. This is an example of what a tiny object can do to a block of aluminum. The projectile in this experiment was made out of polycarbonate and weighed just 7 grams. But when it collided with an aluminum block at 7 kilometers per second, it carved out a crater 5 times wider and 5 times deeper than its own diameter. To understand what goes on in orbital impacts, it helps to look at the impact in stages. As the projectile collides with an object, it decelerates extremely quickly, which compresses both the projectile and the object. As the pressure of both objects increases, the temperature gets hot enough to melt the impact area and vaporize the projectile. The compression sends a shock wave through the object with enough strength to completely tear apart the material. All of this happens in a fraction of a second, meaning astronauts on board the ISS would never see it coming. But there is a new solution under research at the moment that could provide even greater protection for the ISS. While current Whipple shields use Kevlar or aluminum oxide between the walls, it's possible that this could be replaced with a new material that performs something called rapid puncture-initiated healing. This involves replacing the filling of the Whipple shield with a liquid. As the debris passes through the shield at high velocity, the heat and friction will stimulate the liquid to flow into the hole and plug it as it hardens. One test involved the liquid reacting with oxygen, which sealed the hole in less than a second. Shields like these need to be constantly improved as we send humans beyond our field of trackable space debris. Lighter shields that are easier to fix will also be crucial for long-haul trips to Mars and beyond. Either way, we can be thankful that we have an atmosphere here on Earth which protects us every single day. So make sure you're subscribed so you can join in the discussion as we continue to learn more about all things space.